Okay, so let us start today's session. So, so we are continuing our regular problem solving sessions of natural language processing. This is week 5, and this course is taught by Professor Punyajoy, and which is this course is from IIT Kharagpur, and IIT Saha, your teaching assistants for this problem solving session. Now, in this week, we will be mostly covering different parsing algorithms and grammars. So hopefully we have covered the lecture part. Let us move to the first question. The first question, this question we have to identify which of these statements are false. So can anyone tell the answer? The first A part is worst case running time of CYK algorithm is O of NQ, then to G, mod of G, but G is the size of CNF grammar G, and N is the length of parsed string. Is this correct or false? No, I am asking about the first A option. So let us go one by one so that we can understand the reasoning as well. So first A answer, is the answer correct or not? We'll come to the C option later. Anyone tell? So how many of you know the CYK algorithm? Does anyone know? Let us go forward. So the first A option is we have to identify if it's true or false. This is the overall algorithm of CYK. This is the overall algorithm for CYK. And for this algorithm, we basically want to parse a length, a sentence of n length, and or string of n length, and using the grammar G. And then is it condition for the grammar as noticed here is that the grammar should be CNF. CNF stands for Chomsky number. And what we do is we consider a table of for dynamic programming. Then we firstly see if the string is an empty string, then we check if S2 is the root, then we accept the string, else we reject. Otherwise, we have one part where we directly check if there is any terminal. The way goes to terminal, so that part is checked here, and then this part is the main part. So we will come to this algorithm in a while and apply it in real setting. But for now, just try to understand what is the complexity. So these are three parts of this algorithm. So based on this, can you tell what is the complexity of this algorithm? So it is very simple because there is one part where there are two for loops, one where there are four for loops, and the rest of the parts are simple if, which is one. So can you tell which what is the complexity for this? This is we are looking for the host time complexity. Do anyone know what is the complexity for this algorithm? You can write in the chat as well. Hello? Okay, so let us move forward. So we have four for loops. So for each, so if I have essentially if I have one for loop, so that means that the if I have one for loop, that means the program will run for n times. So n is the constant here, and the complexity will be O of n. This is the worst possible complexity. So for nested for loops, we will just multiply the n part. So here there are so here there so you see naive like in at first class there seems four for loops, so you will directly say it is O into the power 4, but that is not the case because the last for loop is for all the rules in grammar G. So that is mod of G. So we have for, for the first loop we will have n into mod of G. Then for the second we will have n cube, that is for three for loops, and then into grammar G. And we have to take the maximum of this, so that will this. So did you get the logic? Reply with the yes or no chat. So that means the first option is correct. There is not false. So you have to identify the false part. So this is not false. Let's move on to the second one. So if CFG G, so CFG is context free grammar, G is in Chomsky normal form, then G is always unambiguous. Is this true? Is this statement true? No. Why no? Let us try to see with an example. For example, if I say have a grammar, uh, imaginary grammar for now, and the English grammar for now. So the man saw the dog with the telescope, and the man saw the dog with the telescope. This can have two different parsing algorithms. One is that the man is seeing a dog with with the telescope, and another is the man saw the dog with his telescope. Here you can notice that all of these have like either all of these grammar parts are in PNF, but still there are two possible ways to parse this. The third part. So, do you think this is true? Okay. Anyone else? let us see. So how to think about this question? So what it says is it requires 2n minus 1 distinct production rules in CNF to generate a string of W of length n. So what can you do? First, let us try to so first we start with a non-terminal symbol S, which has a length n equal to 1. Yeah. So first we start with a non-terminal S, which is length is n equal to 1. Next we have n minus 1 rules of form nt give to nt nt. So what will this do? So let us say we have the first one, that is S. Then we have different nt to nt nt. Now this nt can be different non-terminals, and so you can then extend it to. So this can look like nt2. Then you can break the second non-terminal to again give another such term. And again, see, this is under the Chomsky normal, so that is to be preserved. So that is the second rule. Then finally we have, so this is like n minus 1 rule. And we construct a string containing n non-terminal. And finally, we'll have have the rules like nt to nt to t, which is the final transformation of non-terminal to terminal. So this will have this for this we will have n rules. The first symbol is S, then we have n minus 1 nt, and then we apply this rules n times to get the term. So that means 2n minus 1 production rules. However, the rules that we use here might not be texted. So what this are saying is, our crucial point is that it requires distinct production rules. That may not be true, right? So I can have similar rules doing the same thing. So same like S to AB can be one rule which can be used several times. That is the crucial part. So the rules are not may not be distinct. Hence this is false. So overall this part, this B and C is false. So when you are doing this type of question, try to see if there are multiple false answers, so that can be one careless mistake that you can do. So always try to see if there are more than one false answer or not. Okay. Do you have any doubts in this question? Let's move forward. So consider the CFG given. So this is question number 2, and we have to find out how many non-terminals should be added to convert the CFG into a CNF. Now, what is a CNF? So, can anybody answer what is a CNF? Or when do we call a grammar in Chomsky normal form? There are 3 properties. Okay, let's go to the properties. So the first property is a non-terminal generating a terminal. So all the production rules that is in this CFG should satisfy one of the following conditions. The first condition is a non-terminal generating a terminal, that is x to x, and non-terminals generating 2 non-terminals, x to yz, and finally start symbol generating empty string. So these are the 3 rules that should be there. three rules that each of the production rules in this CFG should follow to call it a Chomsky normal form. So now, how do we convert a CFG to its Chomsky normal form? Let us try to see this process step by step. So first we have to eliminate start symbol from RHS. The start symbol is S. So in this grammar, do you see any statements where there is start symbol in the right side in the RHS part? So in this grammar that is given here, this part, do you see any of the do you see the start symbol at any of the rules RHS? Yeah. Then we do not have to apply or worry about this step. But if there was, let's say, something like this, S or so if this is the condition, then we have the start symbol in the RHS as well. So what we will do, we will use a different rule there, and so now this becomes your start symbol as written. So if you have such case where you have the start symbol in RHS, you create a new rule that is S0 to S. But here we do not have, so we don't have to worry. Now let us move forward. So now eliminate null, unit and useless production. So we have any null productions here? One we can identify P to empty is a null production. So you have to remove that. So as you remember in the original part, only start symbol can generate empty. So that's why we have to remove it. And how to remove it? So this was the grammar, and we can see that. So we apply the rule here. So A given B, B and then a small c. We apply this rule here, so it will become empty. So just C. So we add an additional output here. So C is additional element. Another rule which is having B is this. If you add this rule B to E, it will again become C, and C is already there, so no need to add that. So that's so adding this C will cover all the properties that is given by B to empty production, and hence the null production is removed. Similarly,
can you repeat that, please?
yes. So let us stop or forget about this. Yeah, so what we have first is S to C. So this is one rule. Okay, this is one rule out of this first one. So now you have to remove B to phi or empty production. So what we do is we pass S to replace B with empty production. So this will be essentially this, and this we can also write as C, only C. But we already have S to C here, so I do not need to worry about this part. So we can remove this as is. If C was not there, like this was the condition, then we will add another production, that is C, S start to C. If the production rule is already present, you don't need to add it again. That's the point. Similarly for A to B small c. Here we can again replace it with this character and c, and this becomes small c. Here we can see that there is no such productions which gives us A to C. So that's why we add another rule that gives me A to C. That is the only change. Is it clear?
Okay. Okay, sir. Thank you.
So yeah, so we do not have any other unit production. So what is unit production? So unit production will be something like, yeah, we do not have any other null production. Let us move ahead. Yeah, next we will remove any production which has a terminal and a non-terminal that can be decomposed in the following way. So if we have x to small x and capital Y, where small x is the terminal and y is the non-terminal, capital Y, you can do it in this fashion. So we will have a rule that is x to zy and then z to small x. So here if you see, we have one such rule, that is S to C. Hence we can add another x terminal here and then produce this. So here the rule basically is, I can show it here. So we have one rule that is C. We add x non-terminal xp, and x can give us again c. So this is the step that is hidden here. So we will add xp to this rule and x to c as a separate rule. Is it clear?
Yes, sir.
And then again we have another two similar cases. So here one is CAA, small CA, and AB small c. That can be also handled in similar fashion. So just try to do this and let me know what are the individual uh, decomposition. Like if you have B, CA, AA, what is the decomposed version of that? So use this grammar to find out the decomposed version for B to CA. It is similar to what we have done here. just there are two non-terminals instead of one, but the logic will be exactly the same. Can anyone do this for this rule? Either you can do it for this rule or the next rule also.
Yeah, introduce some y which gives CA so that we have B is YA.
Write the rules in the chat box. What will be the
Okay.
decomposed rule for B to CA using this step 3? Yeah. So it will tell me it is very easy. Yeah, correct. Yes, that is correct. So yeah, so this step is very simple. Then we will do the same for this step. So finally this ends up. So after this, we do not see any other rule which has both a terminal and non-terminal in the RHS. Finally, we will remove uh, such production rules where there are more than two non-terminals. So for example, now there is BXAA. So how do we do that? We use again the same logic that we use uh, a separate non-terminal PZ, and then P can produce X. So if I have the same thing here, what will happen? P, let's have another R, R, and then RA can be X. That is what I have done. Okay. That are all the things. So now let us return to the question. So how many non-terminals do we add to convert the CFG into a CNF? That will two, because we added the final. If you see the final version, we added X and R as two non-terminals. Is this clear? Is this clear? Okay. Okay. Now another variation of CFG is where we have probabilities with the production rules also. That is known as probabilistic context free grammar. Here is one example. So this is the question here. Now we have to do the same. So yeah, what is the equivalent CNF for this probabilistic context free grammar? And now you know what to do, right? So first we have to find the first here we have to see if there is any null production or init productions. The null production I did not see any. There is one init production. So what we can do, we can just replace. So we have one rule here, verb to touches. So instead of verb, we can add, since CV to verb is there, we can directly add